Communication is an essential part in PLC because we need to download our program to the PLC. We need to know what is going on PLC status of each inputs, outputs, or what any configuration what we have made, that status, how to know that PLC works properly, there is no error in the PLC. So through communication, we can have that information. You can see in that image, there are two ports available for communication. One is USB, one is Ethernet. Mostly in USB or Ethernet port, we can download that program what we have developed to automate the machine. Nowadays, mostly we are using Ethernet ports, but in earlier days, mostly RS-232 was used for downloading the program. Then memory is where we are storing the information of all input outputs. We are running PLC program. PLC program has many instructions. What status must be stored while program gets executed. Those information we are storing in memory, and also while program gets executed, what would be the state of the output field devices. That information gets stored in memory, and later on it will be passed to the field devices through wire. So those information should be stored in a memory. There are two types of PLC memory. One is program file memory, another one is data file memory. Program file memory store actually the user-defined program, what program we have developed to automate the process. Data memory file will store our status of input outputs, those instructions what we have been using in PLC programming to develop the logic, those information, configuration of PLC communication, those will be stored in data memory file. Also, we have one system memory. System memory stores system-related information of PLC system, like communication, configuration. If there is something went wrong in PLC, some error is generated. That information system memory stores. So let's talk about PLC architecture. Considering architecture, PLC system has four major parts. One is sensing input or controlling hardware. PLC input section, the controller CPU, which is responsible for execution of our program. Computer are for programming. The devices what we are using, like laptop, to make program and to send it to PLC to run accordingly. Output PLC section, which is wired with our field devices to run the output, and hardware PLC devices, which are field devices itself, such as a motor starter or a pneumatic valve, control valves, such thing. Here is an overview of PLC architecture. You can see on left side, field input devices. Those are can be of 24 volt DC or 230 volt AC. They send such signals, AC or DC signal, considering their source, to the PLC input section. So PLC input section send these signals. It will convert those AC or DC signals. Like, let's consider one sensor which is sending 24 volt DC. So those signals will be converted to 5 volt DC through one isolation, because electronics inside PLC input section can't withstand higher voltage. There is one physical isolation in input section that will be helping to isolate it to higher voltage of field devices to the lower voltage of electronics used in the PLC. So then CPU is responsible for the execution of program. We are downloading our program in memory. Memory will be interacting with CPU. CPU will be interacting with memory to execute the program. There is obviously one power supply section which is used to power entire system, entire PLC system. We'll have one PLC output section which will be used to give signal to field output devices. And programming devices which are used to download means writing PLC to send a program from PLC to our laptop or program devices to PLC. You can upload means we can take what already running PLC program to our laptop to see the status of the PLC program. Addressing is something which required to identify each inputs in PLC input module, or to identify each output which are connected to the PLC output model. It involves also to identification of instruction which we are using in PLC programming, such as timer, digital timers, counters, and move registers. Numerous instructions are there which are used to make PLC program. We need to identify them separately and distinctly. For that, addressings are used. So for addressing, we each make of PLC apply some distinct formatting. Accordingly, they will be addressed. When they are addressed, they keep in mind to have the information of location of that inputs in PLC system, what type of whether it is input or output, which number of points in the PLC input modules or output modules. Those things are those informations are carried by the addressing by the address of the same element of that element. As I said, each PLC manufacturer has different addressing format. Anyway, that PLC that addressing format will say us that all information to identify that PLC inputs or outputs, or if you require to identify that in a program, that instruction can be identified by that addressing. Here it is illustrated how addressings are done in a PLC. I have shown here one of the reputed PLC brand, Allen Bradley PLC addressing. You can see on right side one modular PLC with power supply module on leftmost side, then CPU. Next to that, IOS modules are put together one by one. The location of input outputs in a PLC system is known through slots, through location which are made one next to each other. Like first CPU is placed now in a position which is known as slot 0. Next to that, one module is that which is where that position is slot 1, then slot 2, and it will go on like that way until we place until we finish up placing our modules. On our left side, you can see how we have in Allen Bradley how addressing is done. So first, we can have a look at one addressing. First one is I colon I1.1.0/0. I which defines what type of a module it is. It is an input module, so it is I. So then 1 defines about slot, that location of the module, that is 1. Then 0 is subgrouping of the address of the input points. Here actually 16 inputs are there. If it was more than 16, like it would, if it was 32 input points, then that 0 would be 1 for from next onward from 16th input. So that is subgrouping. And next last points is to identify that exact input points. They are numbered in increment manner 0 to 15. So same manner, if you see output module next to it, it has first letter O to identify that it is an output module. The next one you can see that is 4, because you can see on right side it is placed on slot 4. So to identify the location of that module in the PLC system, we have to name it as a 4. Then subgrouping, and that is a 0, and then that number of points in an increment manner. The details is shown here. First one is IO type, colon. Then next number is slot number, that says that the location of that PLC system. Then subgrouping, or it is known as ward number, where to group them in to group these input points. Then at the end it shows that number of IOs. So as I said, that PLC addressing varies considering a PLC manufacturer. You can see here one PLC manufacturer of Mitsubishi PLC input-output addressing, where instead of I and O, PLC input and outputs are named as X and Y. So on right side, same PLC modular PLC is along with the same input-outputs model, but different addressing. First slot 0. Also, slotting can be different considering the PLC system, whereas in you saw in Allen Bradley, it was CPU was started with slot 0, but in Mitsubishi, first input module start with slot 0. Then here in Mitsubishi also it is in decimal format. Sorry, in hexadecimal format. Then decimal format in Allen Bradley. So they will be in increment manner. So first slot 0 has that PLC input which has 16 inputs. It will go from X00 to X0F. The next one will be starting from the end of first input points X10 to X1F. Consider that it will be in an increment manner. If in between, if any output module is placed, then that will be named with that increment manner, but naming will be different to identify that output module, that is a Y. To identify that you have to give it Y. PLC's scan cycle is a set of rules we have to follow. PLC processor follows to execute the program. So when PLC processor runs, it scans for inputs in the beginning to find out what is the status of inputs field devices. Then it has a PLC program. Processor executes the PLC program considering the input status. Then we have PLC outputs. Program after execution of the PLC program, processor will update that output of output points to the output modules. In turns, this PLC output module is wired with field devices. They will be switched on according to the PLC program. So you can see in the right side, it is illustrated in an image that first we will have in PLC scan cycle, we will have input scan, then program execution, then output scan, then diagnostics, then communication. And this process repeats. Once each step gets over, that process will be repeating until our PLC is in run mode. So let's talk about each scan type in detail. First, input scan. In input scan, when you switch on that PLC, and PLC is connected with field devices. PLC will start running the operation. That time in the beginning, at first, it will see the input device status. So in input scan, all field devices status will be collected by the input module, and it will be sent to the processor in memory, where it will be saved in allocated assigned memory file. That is input scan. Then program scan is where processor will execute the program with the help of that received input signals, input status. Processor, that PLC program is actually it is like a which will have various lines. So PLC processor will execute the PLC program from the first line, from left side to right side, and it will solve the logic in that line one by one, considering that PLC input status, and it will jump next line, then it will solve that line, that program from left to right, and it will jump again to next line. It will keep doing like that way until it gets to end line. In most of the PLC programming, there will be one end line will be inserted in that PLC program automatically. So to define that, to identify that PLC programming is over. Once it reaches that end line, it will jump again to the top line, and it will start again from left to right, executing that PLC program. So while it executes the PLC program from line to line, it sees the instruction which are used in that line. So when it uses that the status of PLC input and the instruction what we are using there, that status, by seeing those status, it will decide whether we have to switch on that output device or not. So it will execute one by one. First, suppose one input points, one sensor signal is there, it will see whether sensor signal is on or not. Then another instruction is there, it will see that instruction status. Then if any other instruction there, it will keep seeing them, and it will see at the end one output element will be there. It will see whether we need to switch on that element or not, and it will keep saving those status of the output in a memory file. That is the same as how it is assigned in input memory file. There will be output memory file where it will be saved. Then output scan. In output scan, it's a processor sees that memory files of output, and those memory file, those status will be transmitted to the terminals of the PLC output model. As field devices are wired with PLC output model terminals, they will be switched on or switched off according to the requirement. How a PLC program is done by seeing that status of output, it will be switched on or switched off. Then diagnostic, which is also important, because while we run a PLC program, we need to know that we have to be careful that nothing went wrong in a PLC system, in its electronics side or in wiring side. If it got overloaded or short circuit happened in PLC system. So PLC software is enough efficient to let you know that if something went wrong in that PLC system, if there is some error or warning. So those things will be updated to your to a memory which we can read through our laptop, through our programming devices, which will be connected to the PLC. Then communication, because we need to know also sometimes the status of the PLC in our laptop. So through this communication, in this communication scan, it will be updating, processor will be updating what is the status of each input outputs in our software, which we will be using in our laptop. So during this process also, it will be updating the status of PLC to the other PLC, which will be communicating to the to our PLC. There will be many peripheral devices, like many other drives, other intelligent modules, which will be communicating to our PLC. Those they will be collecting some data from our PLCs. Those will be updated to those data will be updated to the peripheral devices through this communication scan. So let's talk about some special type of modules which we can be using in our PLC system to make our operation more efficient and more precise. The smart devices which will have their own microprocessor, they can also take decision by their own. So following are some special smart modules which have been used in PLC system. First is communication modules, because sometimes we'll have machines which need to be connected with other machines, so that they will be like to run batch process. One machine finish their operation, then next machine will start its operation. We need to know that when one machine finished its operation, we can have some communication method by which one PLC can know that previous machine operation is finished, so that it can start its operation. For that, specific communication modules are there, which can be used for communication from one PLC to another PLC, or some other devices which will be far from that PLC, cannot be put together in how we put in modular PLC. So there are some specific dedicated modules are there for communication. Then we have also high-speed encoder input modules, where sometimes we need to get inputs from field in fast interval. Suppose let's consider we are counting the rotation of a fan. Their interval of counting will be like some milliseconds. Through our standard input modules, it cannot be possible. We require some advanced modules. Remote I/O modules are used nearer to field devices, unlike modular PLC input modules, which will be housed in a control panel near at a control room. So sometimes we'll have an array of machines, number of machines, which will have similar function. We will have their control panel together in one control room, which will be far from the machine. So that time, if we want to wire their in field devices to the PLC system, it will be requiring a lot of wiring. So that time, what we do, we have our remote I/O modules. As it says remote, it will be not closer to our PLC system. It will be nearer to field devices. From there, in a single wire, we get the status of IOs, field IOs, and we send it to the PLC system. We have also, we can read temperature through RTD, which is used for sensing the temperature inside the machine chamber. We can have the temperature information through some special input modules, that is resistant temperature detector RTD input modules. We can send signals to stepper motors, which to be more precise. PLC module can generate digital pulse train, which are much faster with less interval. Thermocouple thermocouple millivolt input models can read the millivolts from the devices. The thermocouple which are used to measure the temperature, we can have it generates temperature in the form of millivolts, and these millivolts can be converted into readable format to know that what is the temperature measured by the thermocouple. So let's have some idea on PLC software which are used for PLC programming. PLC software is something where we put our command decision together to let processor to know how we want machine to run. So we will have a lot of many instructions like relay type switches, NONC, or timer, counter. Those can be used. Those can be used to make one operation how we require. Each PLC manufacturer have their own softwares with a different name. They may look different, but their core function is the same with that instruction what we will be requiring to make a PLC program. So some PLC programs are most of the reputed PLC make softwares are not free to use. You can download them from the internet. You need to purchase to have license to use them. Whereas some PLC use third-party PLC software, like one is their Codesys, or some PLC make use Codesys to make their PLC program. Some of the reputed PLC software like Allen Bradley or Mitsubishi, Siemens, those are not free. You have to pay some money to get that license to use their PLC software. You can download the PLC software, but you have to purchase the license to run it in your laptop. Whereas some software like of Delta or LG, those are free. You can download them from their site. Only you have to purchase their PLC hardware. You can make your own PLC program and you can download into that hardware. So these are the list of PLC software used by some reputed PLC companies. For example, RS Logix 500 and RS Logix 5000 of Allen Bradley. Allen Bradley is the PLC division of Rockwell Automation. RS Logix 500 is actually older version, and now newer version is RS Logix 5000. Same as GX developers and GX Verse 2 of Mitsubishi. GX developer is older version, GX Verse 2 is recent version. For Siemens, it is Step 5 Micro in Step 7 Semantic Manager. For Delta, WPL Soft, ISP Soft, those are like older and newer version in that manner. And also ABB, Omron, Schneider, Backup, all have that dedicated PLC software to work on their PLC. And at the end, Codesys, which is a free software you can download from the internet, and it is used by various PLC make. So if you buy, let's consider Bosch PLC, you can use Codesys software to program that program and download it to that PLC. Let's consider, let's have some idea on that programming languages, what are used in PLC programming. Those are, we have 5 type of PLC programming languages. Those are ladder diagram, function block diagram, structured text, instruction list, sequential function chart. Most widely used is ladder diagram, and it is most popular because it resembles the hardware relay logic what we have made otherwise using one relay control panel. it resembles exactly like that way. We can have relay NO, NC in a ladder diagram, and we can just make one logic, which is like we say it, logic in a PLC program, that electrical circuit can be converted into a logic in ladder diagram. So it is easier to use because it does not have like conventional coding, which is easier for those who don't have programming background. There are a lot of instructions are being used to develop a PLC program, PLC logic. Mostly, let's talk about some basic instructions which are most widely, most frequently. Just you can't get away from that with that instruction. You need to use them. So let's go one by one. One is beat instruction. Some instructions are coming under beat instruction. One is normally open or examine on. You can see on right side those instructions are drawn, how it will be in ladder diagram. So NO means first one is NO. NO receives when you use NO for a field input devices. This is an input instruction. So when that signal is on from input device, this will close the circuit and it will switch on the output which is connected to this NO. Then opposite to that NO, there is NC, which when you are using NC to represent one input field devices. So in the beginning, by default, it will make that output signal on. But when that input signal is on from field devices, it will stop sending current. It will stop enabling that output. Then one shot is something that when if you want PLC input signal as a pulse, not like continuous, that time you can use one shot. So when you receive input signal, it will not give the output on continuously. It will give only one pulse. The pulse means it will be like around 10 millisecond delay on and off. Output coil, which is actually output for the instruction, which will receive the signal and that logic which is solved, and what is the outcome of that logic in each line will be saved in an output coil, and output coil will be connected to the field output field devices, so that when output coil on, output coil will be represented by one field devices, so that when output coil is on, that corresponding field devices will be switched on. Latch output coil is something even if input signals are stopped, means now output coil depends upon input signals. If input signals are enabled in that line, output gets on. But if you use one latch output coil instruction, that time even that input signals are disabled, still this output coil will remain on until you give it to another instruction. You use for that output another instruction which is unlatch output coil. To that particular instruction, particular address, if you use unlatch output coil, that output coil which remain on in spite of that disabled inputs will become off. So as we had been requiring timer, counter, those hardware control devices to control our machines in earlier days, those things are incorporated in our PLC software. Those are digitally in graphically made boxes. It is represented with, and can drag and drop in our instruction in our PLC program to make a logic. So we have different type of timer instruction here. On delay timer means it will if you run one on delay timer, it will make a delay of some seconds that that we need to define what is how much delay you want in a process, and after that delay it will switch on the output. Okay, let's consider suppose we are in a food processing industry. We are filling a bottle, water bottle. So you need to have that water bottle just right below the water pipe for some so let's consider 2 minutes. So this timer helps there to keep that water bottle there for 2 minutes. That's now first that water bottle has to be stopped there, can be known through input devices like limit switches or sensors. Then we will use through this timer. We will use this timer to stop there for 2 minutes. We will give parameter of timer will have various parameters. One is that giving how much time it should run. So we'll be giving 2 minutes there. It will stop there for 2 minutes. After 2 minutes, timer output will get energized, and it will give signal to the output connected in that same code and some same programming line, and then that output will give signal to, let's consider, a motor starter to move that bottle away. Like that, off delay timer, which is just opposite of on delay timer, where that output which will be connected with a timer will be remained on in the beginning. After the time when timer runs and it the time's up, that will output will be off. So we have also counter instruction, which counts that will count how many tasks has been running. How many it will count the number of tasks. Count up will be running in increment manner. Countdown will be running in decrement manner. There will be also high speed counter, which will count in fast manner, not like with lesser interval. So let's see different makes of PLC. There are various manufacturers are there in the market with different brand name. Each manufacturer have their own software with a different name, but they are, as I said, the core functionality of that software will be same. These are some different make of PLC which are more widely used and more popular, like ABB, Delta, Honeywell, Bosch, Rexroth, Rockwell, Siemens, GE, Mitsubishi, Schneider, Wake-Up. Okay, thanks a lot. I hope you enjoyed this webinar.